is back. I am Hajra Mughal and I'm excited to share more physics insights with you. So let's begin with today's lecture. So students, the objective of today's lecture is to explore the scalar quantities and vector quantities. We will learn the symbolic and graphical representation of a vector, understand the coordinate system and vector representation in 2D and 3D, master the vector addition and its properties. So student, the first question is that what is a scalar? So a scalar quantity is a physical quantity that can be fully described by its magnitude or amount without any reference to direction. Or in other words, you can say scalars have magnitude only, no direction. And now what is meant by the magnitude? Just have an example. It says that the length of the car is 4.5 meter. So magnitude basically is the measure of the amount or size of a physical quantity representing the how much or how big of something. It's a scalar value, meaning it has no direction, only amount, and is often expressed as a numerical value and along with the unit, a numerical value along with the unit. So let's have one more example. Mass of gold bar is 1 kg. 1 is representing a numerical value, kg is representing the unit. So 1 kg is representing the magnitude of the physical quantity, which is the mass. One more example, time is 12.76 seconds. 12.76 is a numerical value, second is a unit, and the combinedly known as the magnitude, and this is the magnitude of a physical quantity, which is time. And the same goes that temperature is 36.8 degrees Celsius. So 36.8 degrees Celsius is the magnitude and the physical quantity is temperature here. So what is a scalar quantity? It is the quantity which is completely specified by magnitudes only. The first question arises in our mind that why do we study vectors? So basically vectors were developed in the late 19th century as a mathematical tools for studying physics. In order to navigate, pilots needs to know what effect a crosswind will have on the direction in which they intend to fly. In order to build bridges, engineers need to know what load a particular design will support. So there are many other technological examples have made vectors an integral part to study physics. Now, what is meant by vector? Let's have an example. A vector is a physical quantity which is completely specified by magnitude, not only magnitude, but it also needs a direction. So, position of California from North Carolina is 3600 kilometer in west. So, position is a physical quantity. 3600 kilometer is a magnitude having a number along with the unit, and west is a direction. So if some physical quantity having both magnitude and as well as direction, then that physical quantity is known as vector. So what is the definition? A vector is a mathematical quantity having both magnitude, direction, and one more thing, very important, it must obey the rule of vector algebra. Means the how we do addition, how we perform subtraction, multiplication, division, they all are different from scalar quantities. So there is some rule, there are some particular rules of vector algebra, so they must obey those particular rules of vector algebra, that physical quantity. If that physical quantity is obeying that particular rules, then that quantity is known as vector quantity. So what are the conditions of a physical quantity to be a vector? It must have magnitude, it must have direction, and it also obey the rules of vector algebra. For example, velocity. We know that velocity is a ratio of displacement over time, acceleration, momentum, force. All these quantities are represented by magnitude. Not only magnitude, they also represented by direction. Representation of vectors. Vectors can be represented in a two-way. It can be represented symbolically and it can be represented as graphically. We will see both the representation of a vectors. So vectors are basically represented by drawing arrows like this. Here you can see a diagram in which a vector AB is represented. The length of that particular line is known as magnitude, which we can know by the help of a ruler. And the starting point is tail and the ending point having arrowhead is head, and the angle with the x-axis showing its direction. So symbolically it is represented by AB along with the arrowhead. Symbolically, a vector is also represented by a bold-faced letter, either capital or small, like this, like capital or small, bold-face. And it can also be represented by a simple-faced letter with an arrow over it. Graphical representation. So, graphically, a vector is represented by an arrow, and the length of an arrow gives the magnitude and the arrowhead points in the direction of a vector. The starting point of a vector is called tail and the ending point is called head of the vector. Cartesian coordinate system, also known as a rectangular system. In this system, we deal with the two-dimensional plane and three-dimensional spaces. So let's start with the basics of two-dimensional coordinate system. A two-dimensional coordinate system consists of two axes, the x-axis horizontal and the y-axis vertical. These axes intersect at the right angle, means 90 degrees at a point, and this point is called the origin. To create a coordinate system, imagine two real number lines intersecting at 90-degree angle. The horizontal axis is usually labeled as x, o, x dash, and the vertical axis is labeled as y, o, y dash. Together they form xy plane, which is a two-dimensional rectangular coordinate system. So representing vectors in coordinate system, Cartesian coordinate system. So to represent a vector in a 2D plane, we need two mutually perpendicular lines, x-axis and y-axis, that intersect at right angle 90 degrees. This forms the xy plane, a 2D rectangular coordinate system. Let's use an example to illustrate this. Suppose we have a vector force of 50 Newton making 30 degrees with the x-axis. To represent this vector, we need a suitable scale, as we can't draw 50 Newtons directly on the paper. So let's assume 1 centimeter is equivalent to 10 Newtons. So 5 centimeter will be equivalent to 50 Newtons. So by the help of a ruler, we can draw 5 centimeter line at a 30-degree angle to the x-axis. So let's move on to representing vectors in 3D space. In 3D, we need three mutually perpendicular lines, x-axis, y-axis, and z-axis, that intersects at a single point known as origin. And we can't draw a true 3D diagram. Instead, we will represent z-axis with the tilted line, because since we are working on a 2D page, okay, so indicating that z-axis is coming out of the page. So to specify a vector in a 3D space, we need to define its direction using three angles: alpha, that is the angle with the x-axis, beta, angle with the y-axis, and gamma, angle with the z-axis. These angles will help us locate the vector in 3D space. Today we will learn how vectors can be added or subtracted. We know that for scalar quantities, if we talk about mass, then 5 kg plus 6 kg will be equivalent to 11 kg according to the arithmetic technique. But vectors cannot be added like this due to presence of direction. Yeah, but if they have same direction, then they can be added like this. So here we use one graphical method which is known as head to tail rule for addition or subtraction. But first we must know about directions. So from origin, if I move towards right, then I'm moving towards east. And if I move towards left, then I'm moving towards west. Similarly, the positive y-axis upward is north and negative y-axis is south. Here you can see from this diagram, the direction in between north and east is known as northeast, in between southeast, southwest, and northwest. Addition of two vectors. To understand this topic, we have considered two vectors A and B drawn to same scale, making certain angles theta A and theta B with the x-axis. Here you can see vector A on xy plane making angle theta A and vector B making angle theta B. Now to add these vectors, we redraw them to some common scale and place them according to head to tail rule. First, I will make x-axis, x, O, x dash, O is origin, and from that origin I will draw y-axis, y, O, y dash. Then this vector A and vector B, I will draw these two vectors on the same scale. First, I will draw vector A in the same direction as shown in this diagram, like this. As you can see, they both looks same. This vector A making angle theta A with the x-axis. Then I will draw x-axis in order to draw vector B according to head to tail rule. Here you can see I have drawn vector B. How we will draw? The tail of the second vector is joined with the head of the first vector. This is the rule. What is the rule? I'm repeating again. The tail of the second vector is joined with the head of the first vector. Similarly, it is making angle theta B with the x-axis because I am adding it. So I have made a reference axis over here. Now I want to add this, so I want some resultant. So this is the resultant, and resultant is drawn like this by making a vector joining the head of the second vector with the resultant vector and tail of the resultant vector with the tail of the first vector. This is known as resultant, and it is also making angle theta R with the x-axis. So our resultant equation will become R equals to A plus B. Joining the tail of the first vector with the head of the last vector will give another vector, which is the sum of these vectors, called resultant vector. The resultant will have the same effect as the combined effect of both vectors. So we aim to prove that the addition of two or more vectors is commutative, meaning the order of addition doesn't change the result. In algebra, the commutative property states that a plus b is equivalent to b plus a. So we will explore if this property holds true for vectors considering their directional nature. So to demonstrate this, we will use graphical addition on a coordinate plane with x and y axis. We have two vectors a and b. Using the head to tail rule, we add a and b by connecting the tail of b to the head of a, resulting in a new vector r, making angle theta r with the x-axis. Now let's reverse the order and add b plus a. We create a parallel vector a, which is known as free vector, and b. Using head to tail rule, we will add b vector into a, and we see that the resultant vector is identical to r, making angle theta r the same angle. So since the resultant vector are the same in both cases, so we can conclude that a plus b is equivalent to b plus a. This demonstrates the commutative property of vector addition, proving that the order of addition doesn't affect the result. So the second property for the vector addition is the associative property, which states that when we add three or more vectors, the order in which we add them doesn't change the result. Mathematically, this means that a plus b is plus c is equivalent to a plus b plus c, bracketed. Okay, so to prove this, let's consider three vectors a, b, and c, and we will add them in different orders and show that the resultant vector is same. So first we add, okay, let us give the corner points the name as O, P, Q, and R. Okay, so first we will add A and B using head to tail rule. So A has been added into B, and this is the resultant vector known as A plus B. Okay, and then we will add A plus B into C. So the resultant vector is R. And how we will make R? By the tail of the first vector, which is a plus b, to the head of the second vector. Now again, what we have done up till now, we have added a plus b, and then we have add c into it. Now if we reverse the order, first we will add b plus c. So b plus c is added, so we will get a line here. Okay, so b plus c, and we have to add a now. So this is the a here. If I add a into b plus c, then by head to tail rule, then you can see that the head of the a is joined with the tail of the b plus c, and the resultant is again same, which is represented by or. And how we will make this resultant? By the tail of the first vector to the head of the second vector, and this is represented by this equation. So when you have added a plus b into c, then you have got this resultant r. And when we have added b plus c first and then a, then we have got the same resultant r. So we can conclude that the a plus b plus c is equivalent to a plus bracketed b plus c. Okay, so this property allows us to add more vectors in any order, making calculations more flexible and convenient. That's all for today's lecture. This is the part 1 of the video, and in the next video we will be discussing some types of the vectors and the addition of vector by some other methods. Thank you so much.